smart city. Those are the people contracted for the San Diego Convention Center, and they control the price. They control the bandwidth. They control all
Is it just
of
me
that.
on this thing, or fantastic? How's it going? On Tuesday night. Bad. I was gonna come. You are here. And enthralling. Telling no matter what. So thank you. From this room. Yeah. It's the first time you've done it? I was here. 5 focus. We live across town. Gas stamp is fun, but parking's hard. By the way. Yeah, just saying.
Yeah. Sorry. No, no, no. Room 2. All right. But you don't want this? No. What do you want? Did you delete like shift delete? Yeah. Yeah, I got it. That? Yes, I do.
Isn't that weird? Watching the craziest words you said, like that you craziest stuff.
Right.
Craziest, like catastrophic. Some dude. But that was when I thought of when I looked at it.
I'm gonna bring it up now.
Good morning, everybody. Here in the room and those on Teams, welcome to the second day of Dawn CTO Emerging Technologies Tech Track. Going to kick off this morning with Mr. David Gross. He is Next Gen Com, and he's going to be talking about software-defined platform use cases, specifically hypersonic and RF signal sensing. It should be a very exciting brief. So, David, thanks for coming. Came from North Carolina via Boston and arrived here yesterday. So welcome, David, and please, over to you.
Jeff, does this work or only this? Okay. Good morning, everyone. I appreciate everyone coming this early. Okay, so we'll start it off by a rather unknown military. Oh, sure. My name is David Gross. I'm Director of Product Marketing for Next Gen Com. We're based in the Triangle, Research Triangle Park. There's a slide that deals with our specific expertise, and I'll get to that in a little bit. But so just to kind of set the paradigm or theme of this presentation, we start off with a rather unknown general who said famously that the battlefield is a scene of constant chaos. The winner will be the one who confronts that chaos, who controls that chaos, both his own and the enemy's. So, okay, so with that being said, I apologize for the setup. I think you can all hear me if I just talk like this. Yeah, is that okay? Okay, cool.
Light on.
Oh. Yeah, okay. Is this okay? Oh, okay. Okay, so today, so taking that quote into perspective, the question becomes how to best control that chaos. And controlling or quote-unquote managing the chaos may be a better term, but controlling depends on data inputs and synthesizing data inputs depending on the amount of data and the timeliness of said data. Therefore, as you can see on this slide, we have two important criteria categories that we use as an example: throughput and latency. And here are some examples of what the DoD and the Navy largely use them for, you can see. And therefore, you can come to the conclusion that there's an unrelenting and exponential increase in the amount of data required and a corresponding reduction in the latency required. However, what is an effective and efficient way to keep up with, what is an effective and efficient way to keep up with these requirements? So one answer to that question would be to tap into the commercial sector. And as you can see from this chart, the DoD started off far more advanced. You can't see the mouse, okay. But as you can see from this chart, the DoD started off far more advanced than the commercial sector. However, there was an inflection point in the 90s and early 2000s where commercial wireless, specifically cellular, surpassed the DoD in capability pertaining to our two criteria here that we use as an example. They are able to achieve, the commercial sector, a price point and capability in a small form factor that it's very difficult for the DoD to match today. And nothing I'm saying is especially groundbreaking. There are many programs looking to ride, quote unquote, the commercial wave and leverage the latest in commercial technology. However, I would argue that the DoD can still get siloed in its thinking regarding the diverse set of use cases or ConOps it is responsible for. That drastically different solution sets are required to get the job done. And this type of thinking prohibits the DoD from building up substantial volumes and gaining access to highly capable hardware that is available today in the commercial sector. So, what is required, in our view, is a common communications platform that meets DoD latency and throughput requirements and can be leveraged. And if the battle is truly controlling chaos, then broader pipes with lower latency to convey the data for synthesis is an advantage we cannot do without. And we use that, we can take our commercial communications platform, the M5NS, which I'm going to go into more later. It's a common software-defined platform. And I'm going to show you today of how you can use it for two very distinct and diverse use cases. Okay, the hypersonic data link, or bidirectional hypersonic data link, and RF signal sensing for data collection. Again, a commercial platform that's used for both and everything in between. So very quickly, a little bit about our product platform, the M5NS JCP, Joint Communications Platform. It's a COTS integrated platform, and it supports a myriad of different waveforms, right? Right now it supports 5G, we're porting MAN-A. It's capable of supporting everything that you see there, almost all commercial waveforms, as well as a good amount of DoD waveforms, MAN-A, CDL, MADL, Link 16, and SATCOM. It also is capable of functioning in different roles or domains, meaning it can function as if it's on using 5G parlance, so or 5G terms. It can function as a base station. It can also function as a user device or as a relay. In addition to that, it can function as an RF sensor or EW node, which we're going to be talking about today. Okay, it's available today. This exists in several different SKUs. There's an 8x8 inch and 6x4 inch. Again, very small form factor. Okay, and we're going to a smaller platform that's a 4.5 by 3 inch and 3 by 2 inch. That's very low power, and everything is very low power because we're leveraging commercial hardware, and we come from the commercial world. So these swaps, if you will, size, weight, and power consumption is unmatched today. Okay, so let's get into a little bit about one of the topics that we're talking about. Okay, so what are the issues with low latency hypersonic broadband data links? Okay, well first, why would you need it? It enables real-time or near real-time command and control. That's a good answer. And it enables proper testing and simulation, right? So if you're testing this thing, how do you figure out or determine whether it's functioning properly or not? So one benchmark to use is commercial aircraft generate a tremendous amount of data, right? So, and this is freely available online. Typical commercial aircraft, meaning like a 787 or A350, will generate anywhere from 1 gigabyte to 1 terabyte of data per flight, depending on the components, aircraft, and number of sensors. So this means, you know, at a minimum, you're looking at several hundred megabits per second of data, a throughput requirement at the very least. So there is a utility in that kind of link, but the question is, what are the issues with making this happen? Okay, first is obviously the velocity of the hypersonic platform. Okay, sources available online give an approximate top velocity of Mach 10. Probably the people in this room would know that velocity better than I or my company, but that's just some freely available information that's online. The Russian supposedly is something that goes up or above Mach 20, but obviously that's questionable. And again, you guys would know better than I. But the bottom line is you have to communicate with something moving very fast, and that has a whole host of issues. Second is its altitude, and that affects the look angles, and that we'll get into that more when we're talking about whether we're communicating from a terrestrial station or a LEO in this example. The next point is that obviously the big one is the so-called plasma sheath, right? And the plasma sheath, if you're familiar with hypersonic platforms, you know this phenomenon very well, and I'm sorry for repeating it if you do. But for those that don't, the plasma sheath is a phenomenon where friction causes ionization to occur, and basically it prevents most communication systems from working or being able to pierce that sheath. It's also called something, there's another term it's known by called the blackout barrier. And again, it basically prevents any sort of communication depending on the speed or velocity of the hypersonic object as it's traversing the atmosphere. So a very basic or simplistic way to look at this is the higher the altitude, the lower the friction because the atmosphere is thin. And so you have less ionization, and so you have lower attenuation. The lower the altitude, the thicker the atmosphere. And again, I'm not the expert. We have several partners that are the experts on this specific phenomena. Um, but the lower the atmosphere, the greater the friction, and the higher the attenuation due to the ionization of the plasma sheath. So that is obviously a very big issue. Following that, right, you have, depending on the frequencies you use, you have an attenuation problem, just from a general standpoint. Propagation of certain frequencies prohibit their use, especially at long range where it's of any utility. All right, so basically what I'm saying is that if you look at most online available literature, the frequencies that you need to use most likely range and go up to 150 or 200 gigahertz, which prohibit their use, especially in any sort of long-range system. All right, so the question is how exactly do you sidestep, if you will, that sheath, right? The fourth big issue is what is the high Doppler shift due to the velocity of the hypersonic object, right? This creates all sorts of issues, especially when it's amplified by the frequencies that you're using. And the fifth and also big issue is, well, obviously you need to employ, especially at long range, some sort of beamforming or beam tracking. All right, and therefore this hypersonic object is moving very fast, and that also and it's moving at a difficult to predict trajectory, and therefore it can be difficult to line up those beams and make sure that you close the link. And the last issue that you're going to have to deal with, just generally speaking, from a hypersonic projectile, is the swap. Okay, you need to make sure that whatever you put on that thing, it is capable of handling. The power consumption is not greater than the platform can bear, and also the size and weight are not prohibitive or don't affect negatively the aerodynamics of the object, right? So that's just baseline, the issues that you deal with when you're trying to communicate with a hypersonic object moving at Mach 10. Okay, but then in addition to that, what are you using to communicate with it, right? There's terrestrial, and then there's also there's a terrestrial-based scenario, and then there's a LEO-based scenario. So first, we'll talk about the terrestrial. So the terrestrial enjoys some advantages, right? It's a stationary object, or sorry, stationary location or static location communicating with the high velocity platform. But it is you have to deal with a significantly greater plasma sheath, or just in terms of the friction that it's generated, because the atmosphere is thicker. Right, at least one end of that link has to deal with that issue, right? And then you have all the other issues where you're dealing with high frequencies, trying to communicate in atmosphere, rain, clouds, what have you. It really plays havoc, and so the terrestrial is a very difficult problem to solve, right? Which is why we're going to focus more on the LEO. And the LEO suffers from, or rather enjoys a couple of advantages over the terrestrial, right? First is that one end of the link at least doesn't have to deal with all those atmospheric issues, right? But then the second part of that is that, obviously the thing it's talking to still does, but then this is where altitude comes into play. So if you're communicating with something that's moving at roughly 30 kilometers or higher, the atmosphere tends to be thinner. Therefore, there's less friction, therefore less ionization. Therefore, it's easier to close a link with a manageable frequency. And I'm sorry to say we're not going to divulge the frequency here in this forum, but it's able to close the link at a high frequency, and I'll show you the results of that in 2 slides. The idea is that you can do that and still sidestep the plasma sheath and close the link with enough data that it's actually viable or it's worth the effort. Now, there are additional issues, right? The hypersonic object is still, or platform is still moving in an unpredictable trajectory. However, the LEO typically is not. All right, so that's a very predictable trajectory. So that takes some of the guesswork, or at least reduces some of the complexity from the beamforming and beam tracking standpoint. You have an increased Doppler compensation issue, right? Because you have a LEO, at least, again, it could be a MEO or a GEO, but again, we looked at a LEO specifically. And the benefit is, well, the difficulty is that LEO is moving very quickly, right? So approximately Mach 23, and it's communicating with something, let's say Mach 10 or below. You guys are, I'm sure, are very, very smart. You can do the math. and then determine that that Doppler problem is not an easy one. However, there are some other advantages. For example, LEOs, it's easier to potentially have a network, if you will, of systems that hand off connectivity or coverage to the missile in real time. So as the missile is traversing, as it's traversing over the across the atmosphere, right? It can hand over just like your cell phone, right? In a cellular network, it can hand over between each individual LEO, and thus you have constant and resilient connectivity all the way from launch to terminus. So, okay, so that's basically all the issues that exist. Well, a summary of the issues that exist. There are many more, but as a good summary of the issues that exist with trying to ensure bidirectional communication with the hypersonic object. So a little bit about plasma and atmospheric attenuation, okay? Basically, the issue is, well, it's more or less what I've already described. The way you have to deal with that is obviously you have to study the problem, and you have to get a good idea of exactly what would work. But essentially what's required, especially when you're dealing with an object moving at Mach 10 through atmosphere, you need to have a specific frequency or set of frequencies that are able to sidestep that or get around that plasma sheath. I don't like using the term pierce because it's a misnomer. You need the right frequency that sort of, like I said, sidesteps or transcends the plasma sheath. So what is it that we are looking at using? A specialized ceramic material that has only been recently discovered in the last year or so, and it allows you to harness something called plasmonic resonance. Plasmonic resonance is, well, in layman's terms, and believe me, I am a layman, it allows you to shine a very small or microscopic laser, and then that allows you to upconvert into a frequency that will meet our requirements here for closing the link, right? Now the issue is that with plasmonic materials, their point of instability is about 1,000 degrees Celsius. So that's why we need to harness a different ceramic-based material that allows us to employ or utilize those same peculiarities or characteristics of plasmonic resonance, but not in a typically plasmonic material, right? And that can go up to 2,000 to 3,000 degrees Celsius, which is sufficient for, and this is without any sort of additional heat shielding or anything like that. So that's sufficient for closing the link at these very at these high temperatures and at that range, right? And so we're giving you a very brief, set of study and analysis of how you would, take either a blunt or cone-shaped dependent plasma sheath. What's the temperature that you're looking at there? And obviously, spoiler alert, you're not on the nose. That's helpful. But then we lay out exactly or roughly how we would deploy a beamforming antenna on the high velocity object, the rocket. Oh, oops. Okay, so a little bit more, right? So what's the link that we're using, or rather the waveform base that we're using to show it? It's a NTN or 5G plus NTN feature. It is based on release 17, and essentially what a 5G NTN is, it stands for non-terrestrial network, and what that enables is for connectivity with fast-moving LEO satellites with your smartphone, or something else called a VSAT, which in cellular terms is not probably the way you know VSAT. It stands for very small aperture antenna, which is essentially just a higher output power version of your smartphone. And in this standard, it accommodates things like Doppler shift, because you're communicating with something moving, a LEO, at Mach 23. It also has sort of already baseline features for beamforming, tracking, handover between different satellites, accommodates long propagation delays, and and ensures robust and stable connectivity. So that's the baseline waveform that we were using to close the link at a very long range with a hypersonic projectile. So so what does this all sort of equate to, right? If you bring these together, if you bring 5G NTN, you bring a advanced antenna made of newly discovered materials that harness plasmonic resonance at range, and you utilize a LEO-based link. Oh, this is essentially what you have, right? So you're able to achieve throughput of 1 gig in both directions from the rocket or the platform, and at ranges of 750 kilometers, where the LEO is covering approximately 1,000 kilometers, right? So imagine, if you will, you have a constellation of LEOs. And obviously this depends on your constellation density, right? The more LEOs you have up in the sky, you may have smaller coverage areas, but it's really up to you. But you have a minimum LEO coverage diameter of 1,000 kilometers, and the latency that you enjoy, again, using the M5NS, our existing platform, with the right antenna, you enjoy latency of 20 to 60 milliseconds, which is real time or near real time, depending on how you classify it. You also accommodate a very high Doppler shift, which we discussed. You have something that's Mach 23 communicating with something that's moving up to Mach 10. And then you have obviously beamforming and beam tracking in order to make sure that you're able to close the link, again, with that very, very high frequency. Okay? We have a high accuracy clock that maintains sync without GNSS. Ideally, that's important, especially if GNSS is being jammed. And we can get into more of that in a little bit. And then the idea is, well, what I already mentioned is that you have a networked LEO that maintains connectivity as the hypersonic moves along. So that's hypersonic, okay? So that's one piece of the puzzle, right? But then another completely orthogonal use case is RF sensing, right? So if you have a existing platform that's already capable of handling most of your communication needs, what else could you utilize it for, right? So what would you need it to do, right? So you need it for wide spectrum monitoring, you need it for direction finding, right? Your operating environment is somewhat severe, right? You're looking at maritime or literal propagation handling. There's all sorts of things that you would need this for, right? So again, the same system hardware, which will allow the Navy or the DoD in general to increase the volume or scale, and then achieve some highly integrated solutions that will work for it. So, all right, so this is what we have today in this form, right? So PSD, IQ processing. We have a very potent sniffer, if you will, that sucks up all IQ in the area. And then the only question is what do you need it for? How fast do you need it to process that data? What's the bandwidth? Arguably the most important thing that you need to, the most important thing that you are concerned with, depending on your use case. And then how do you encrypt that information, right? So basically, this lays out the 3 different configurations that you can utilize. Again, the same exact communication system that you're utilizing for hypersonic communications or any sort of mission communications or tactical communications. You can utilize that for an RF sensor. So the idea is that you have you can utilize it in 3 different configurations, either 1 to 800 megahertz. That means you can suck in or take snapshots of 100 to 800 megahertz. Of bandwidth at a shot, and I'll get into how long is that snapshot in a little bit. Or you can suck up 3200 megahertz in a shot, or you can suck up 4800 megahertz in a shot, right? So that's that's purely depending on your requirements and how well, basically. I'll show you how modular the architecture is in a little bit, but this enables you to pick and choose what your bandwidth requirements are. Right, and this is paired with a 2-stage filter, if you will. First is basic first-order analysis and decision-making, okay? Meaning it views, and the next slide details this, it views whether or not there's any signal to be listened for and processed or not. And if there isn't, you have the option to discard it. And then the second stage filter, if you will, is okay, what are we looking at here? What kind of signals are we looking at, right? And we use a deep learning neural net engine to do that. And that's flexible. People can, our customers can train that as they will. But that includes such triggers as geofencing, timing, or direction finding, right? And again, this is a very, very low swap solution. It's again, 4 to 6 inches, or 4 by 6 inches, or even smaller, right? So, what kind of modular architecture are we looking at here, right? So there's two different, basically two different kinds, but the idea is that for each configuration, it's just a function of stacking different modules, and then you maintain your original size, right? So actually, for just the sniffer, if you wanted to use the same platform as the sniffer, it's 4 by 4 inches. I have a bare board here if you'd like to see after the presentation. And then there are two additional configurations, right? So there's 3.2 gigahertz or 4.8 gigahertz, and that's just merely a function of you stacking additional modules, both on the baseband and on the receiver side. Okay, hopefully that makes sense to everyone. All right, so more on the ISA was what we call it. It's called the Intelligent Spectrum Analyzer. So what you have here on the right is stage 1. First order analysis and decision making. Basically, you're viewing whether or not there's any signal in a given bandwidth, right? So the subbands are configurable from 25 kilohertz to 1.92 megahertz. And then you can sample that up to 1024 bits per subband. So you have fairly good resolution on your sampling. But again, you view it and say, hey, is there anything there for me to listen for, right? Then the next, if there is, then that's where things get more interesting. Okay, you can start looking at, okay, what are the properties of specific signals? Do they have specific cyclostationary properties? What are the emitter characteristics? You have your basics, power, PSD, and what's the shape, what's the modulation scheme, what have you. But then you can really start diving into exactly what we're looking at here. Right, and then you can apply geofencing, DF, timing, what have you. And you can do it very, very, very quickly. So what's a little bit more, right? So this is the basic stuff, right? So you remember, we want to know exactly how quickly we're looking at something, right? So the snapshot is 10 microseconds. So you're looking at 10 microsecond snapshots, and then you're tuning every 100 or less nanoseconds, right? So you can very quickly go up from DC to 72 gigahertz at a shot. Okay, and you can store that locally, or you can send it back to exfil that data to wherever you need it to go. Right, and again, the device size at that for that configuration is 4 by 4 and 13 to 18 watts. But here's the other thing that's very important. If you see in that lower row, the synchronization row, it's there's a very high, so we use GNSS, you can use cellular network-based signal sync or for synchronization, or digital TV. But then there's also, if let's say you don't have access to any of those things, right? There's a very high accuracy clock that syncs at within 200 picoseconds of the source, and then it maintains that for up to 48 hours with plus or minus 4 microseconds. That can be approved, and that's over 48 hours. That can be approved to 96 hours, we believe. But that's what we've done and accomplished in testing, right? But yeah, and then the question is, what happens when we start really increasing it, right? So here's where things get also very interesting, right? Because there's basically several different configurations depending on the number of modules you have stacked. So if you're stacking, if you want to you want to look at 3.2 gigahertz at a shot as you go up from DC to 72, I mean, that's fine, then you work your way through. But let's say you want to look at multiple different steps, if you will, simultaneously as you work your way up through. Well, that just depends on the number of modules you'd like to stack, right? So what we're offering here is a very, very fast and tunable RF sensor that allows you to see anything from DC to 72 gigahertz. And a very quick, and it's running constantly. So it's at a very small form factor and power consumption that is unmatched today. Yeah, and this is what happens if you're looking at 4 simultaneous channels, right? So this is where you have your bandwidth duplicated. Obviously, that grows in terms of size and weight. But that's pretty much it. Okay, so you may be asking, what exactly is the platform that's capable of doing this? I showed you something about it before. Here's a little bit more information about that. Okay, this is at its base what it's comprised of. So you have your JCP, your front end, your RF front end may or may not be included in the JCP. It is here, but that obviously depends on the requirements. But you have your baseline transceiver or transceivers, which is capable of supporting 4T4R, 8T8R, and again, you just sort of stack them. You have a highly capable ASIC-based DSP, which is capable of supporting, like you were showing, 5G, MANA, Link 16, saddle, mattle. I mean, whatever it is you're looking for. And then you have a highly capable SOM, right, which is an MPU, or stands for Network Processing Unit. And that is where higher layers of communication exist. But that's also where in this instance, right, your intelligent spectrum analyzer sits, as well as your management system, TAC server, and your post-quantum encryption, which is something we have today, FIPS 197 and 203 compliant. Yeah, so as you can see here, you see the type of FFTs and IFFTs and FFTs that we employ. And again, that's mostly in an accelerator. So again, very tightly integrated, very low power, but highly capable, and that's what we use here. A little bit about us: we have Next Gen Com is in RTP, North Carolina. We have about 25 plus employees, 90% engineering, and our core expertise is the guts of the communication solution. Right, so basically layer one, the DSP physical layer, and then the protocol stack. So that inner guts of the way your modem interacts with the base station and the way the base station interacts with the modem. That's where we play, and that's our expertise. So that's it, Brian. Thank you.
Awesome. Thank you, David. We have time for questions, and I'll just kick it off. You spoke a lot about LEO. Do you have relationships with any of the LEO providers? Amazon Kuiper is going to be here briefing, and not the next hour, the one after. And then, of course, SpaceX, Starlink, Starshield.
We have relationships with vendors for those LEO providers, is the way I would say it. Like people that build the satellites, and so we put our payload on there, and that works.
Okay. Questions? Questions from the audience? In the back there.
So in your beginning slides, I think you had a use case with a military unit. Could you explain that?
Which one?
It was towards the beginning of your slide deck. Keep going. Yeah, this one right here. Yeah, can you explain what unit was using this and what was it
18th
for?
Airborne.
Okay.
18th Airborne of Fort Liberty. So we do. We're in a couple programs. We're with OUSD. We do work with Joint Staff and 18th Airborne. That's what that one's referring to, and some others.
Okay. Do you have any specifics on exactly what they're using the equipment for?
Yeah,
Or
sure. But
just wanted to go through
yeah,
that.
can we talk after
Yeah,
the?
for sure.
Yeah,
Yeah,
that's great.
So thanks, Dave. You talked about relationships. Do you have ongoing contracts with those different organizations?
Yes.
Great. So they're not just pilots, they're actual
No.
existing contracts?
Yes.
Great. Outstanding. So if anybody wanted to get to you, you have existing contracting vehicles that they could probably leverage. Perfect.
I was nodding. Yes.
Yes.
For those that were
Yes.
listening.
Good. Questions? Questions, sir?
On your hypersonic example, I walked a little bit late, so I maybe missed this, but was that where you gave the example where you were able to close the link using the 5G NTN? Was that proven through an actual demonstration, or was that theoretical?
It has not been proven yet. It is. We tested, we simulated it, but it has not been proven yet. If we had, you probably would have read about it somewhere. So, but no, not yet. We're looking for opportunities to do that. It seems like, not to editorialize over much, but it seems like this requirement is not, let's just say it hasn't trickled down yet. So there's conversations with different constituents that participate in the hypersonic programs in DoD. And there's a desire that we've seen for that kind of throughput, but it hasn't trickled down into actual requirements yet. And so we're relegated to informing and sort of educating that this is what's possible. So that's where this is. So it just seems like, as far as we know, they're depending on rather old or antiquated communications with limited throughput. And so, but again, it's not a requirement yet. That's where we are, as far as we know. But I'm open to having a conversation later about, yeah, okay.
David, thank you. Thanks so much for your presentation. And for making the trip. Thanks so much. Please stick around the rest of the day. We're going to be some excellent presentations on quantum, post-quantum. Next presentation, Dr. Arshang Angustari. Is Arshang here? Yes, okay. So Arshang, it's up to you. We can take a break or we can go right into it. All right, why don't we do a 5-10 minute break and then we'll kick it off. Thank you.